Okay, chapter 6 is fields and forces. This chapter is basically divided into three parts: gravitational part, electric part, and magnetic part. So remember, this is an SL topic. So the gravitational and electric parts have been first discussed here, and then in an HL topic. So for example, the forces and field strengths, etc., that domain will be discussed in this chapter. Then potential and potential energy in gravitational fields and electric fields, that will be discussed in another topic, which is the HL portion. Okay. So let's take this part by part. First part, 6.1, is gravitational forces and fields. So explain to the student what gravitational forces are. Any two objects with mass in the universe, okay, will basically exert a force of gravitation on each other. Now let's call this mass 1, okay? Let's call this mass 2. Or, okay, to make things better, let's call this body 1 and body 2. So over here, let's say body 1 is of mass m1 and body 2 is of mass m2. So body 2 will exert a force on body 1. So force exerted on body 1 due to body 2. Okay. So this is the gravitational force, and it is always an attractive force. By Newton's third law, we know that if body 2 exerts a force on body 1, body 1 will exert an equal and opposite force on body 2. So therefore, body 1 will exert a force F21 on body 2. Okay, and like we said, from Newton's third law, we know that these forces are equal and opposite. Okay. Now, therefore, the magnitude of these two forces are equal. Okay, and this magnitude is directly proportional to the product of their masses. Okay, and it is inversely proportional to the square of the distance between them. Okay. Now, when I say distance between them, I mean the distance between the center of these masses. Okay? And this proportionality sign is replaced with a gravitational constant. So this here is the universal gravitational constant, G, capital G, m1, m2 over r squared. Okay, so that's the magnitude of the gravitational force. Now, we should let them know that this has a value of 6.67 times 10 to the power minus 11. Again, this is going to be provided in the data booklet, but what's most important is that you explain how to get the units for this. Again, on one side you have force, which is measured in newtons. On the other side you have this, you have meter square, and you have kg square. So when you bring kg square to that side, it will become kg inverse square, and this meter inverse square will become meter square. So your units will be Newton meter square kg inverse square. Okay, so that's the value of the universal gravitational constant. Now, so any object, for example, a man standing on planet Earth, right? Okay, Earth is going to attract the man with a force of Gmm over r squared. And notice that this force is concentrated at the center of gravity of the man. Okay, r here is the distance between the man and the center of the Earth. Okay, m is the mass of the Earth, small m is the mass of the man. Okay, again, the man will also attract the Earth with the same force in the opposite direction. So, so that is gravitational force. Now, if I want to standardize, if I want to have a standard of measuring how strong a gravitational field is, what I will do is, I will place a mass, I will place a unit mass, a mass of 1 kg or any unit mass. So let's say 1 kg for example, okay? And let's say the distance between the center of the mass whose gravitational force we are measuring, okay? And this mass is R, okay? So at this point now the gravitational force, okay, the force of gravity on this Fg will be equal to Gm times 1 kg, okay, over R square, okay. So in this case, this is the definition of the gravitational field strength by this mass at this point, okay. So the gravitational force on a unit mass at this point, at any point in a gravitational field, is called the gravitational field strength. So this is denoted by small g, and it has a value of Gm over R square, where m is the mass of the mass in question and R square is the distance between the center of that mass to that point in the field. Now, therefore, you can see that this one is simply the gravitational force on a mass divided by the mass itself, right? Now, for definition purpose, we know that this is a unit mass, but this unit mass needs to be ideally concentrated at a point. So what the definition would suggest is that the gravitational field strength is the force per unit mass on a small mass, because a small mass would be more or less concentrated at a point. So the force per unit mass on a small mass at a point in the gravitational field. Alright, that would be the proper definition of the gravitational field strength, G, small g. Right? So again, this is the force per unit mass. Force is measured in newtons, mass is measured in kilograms. Okay, so G here is measured in newtons per kilogram. Again, from Newton's second law, we know that force per unit force per mass, okay, would actually be the acceleration. So therefore, this small g is not only the gravitational field strength, okay, it can also be understood as the acceleration due to the gravitational field. So you can also understand this as the acceleration due to the gravitational field. So, so if, for example, the gravitational field strength is 10 newtons per kg, it can also mean that at that point in the gravitational field, there is an acceleration of 10 meters per second square on any mass. Okay. Now, since force here is a vector, okay, gravitational field strength is also a vector. So let's say that I have two masses, not just one mass. So the gravitational field strength at this point, due to this mass 1, let's say, is G1. Let's say I have another mass over here. Okay. Now I want to measure the gravitational field strength at this point. So I will have to firstly see what's the gravitational field strength due to this mass. Obviously, since this is a bit further away, right, and we know that G equals M1, G equals Gm over R square. Let's say this is M2. Let's say M1 is equal to M2. Okay, so the only difference here would be the R. R here is larger, therefore G2 will be a bit smaller, right? you can represent that by the length of the vectors. Now, if you want to calculate the total gravitational field strength at this point, let's say point P, you will have to do a vector addition of G1 and G2. Okay, the resultant then would be somewhere here. Okay, this should be the resultant gravitational field strength at point P. Okay, so remember, field strength, gravitational field strength is a vector quantity. Okay, this is very important because drawing a parallel with gravitational potential, which is a scalar quantity, you will have to recognize that those two have to be added and added in different ways. For a scalar quantity, you're just going to add up the values, but for a vector quantity, you have to do a vector addition. Okay. So that is that. And 6.1.4, gravitational field strength at the surface of a planet. So let's say planet Earth. What would be the gravitational field strength at the surface of planet Earth? Let's say this is Earth here. Alright. And this distance is, of course, the radius of the Earth, right? So let us assume that the mass of the Earth is concentrated at the center of the Earth. Okay, mass of the Earth. Okay. So for a point here, the gravitational field strength G will be given by G me over re squared. Okay. From the previous part, you just know that this is also the acceleration caused due to the gravitational field at this point, which is at the surface of the Earth. And we know that that value is 9.81 meters per second square approximately, right? So therefore, you can see that this value here is not only the gravitational field strength at the surface of the Earth, it's also the acceleration due to gravity, okay, at the surface of the Earth. Now, in this special case, we can call this G naught. Alright, so G naught has a value of 9.81 meters per second square or newtons per kg. Now, if I had to raise an object to a height h, right? Let's say this here is height h. So then the gravitational field strength at that point would be Gme over r plus h whole square, re. Okay, so we can see that if the height that the object has been raised to is very less compared to the radius of the Earth, we can actually just ignore that and have the same value for G as that at the surface of the Earth. So for a fair distance above the surface of the Earth, we can consider that the acceleration due to gravity is approximately constant at 9.81 meters per second square. So that takes care of the part 1. We'll now move on to electric force and field.